for black hole.
Okay, good afternoon. It's an honor to have a chance to give a talk here. Okay, my name is Chia Jui Chou, and I'm from NCTU. Today I'm going to talk about holographic entanglement entropy and black hole entropy. It's a progressing work with my advisor, Professor Yang, in NCTU as well. Okay, here's the outline of my talk. First, I will introduce what is holographic entanglement entropy. You see, how do we calculate the holographic entanglement entropy of a d-dimensional conformal field theory using the d+1 dimensional ADS spacetime. Okay, and then I will show you the case. We have calculated the pure ADS spacetime, which means there's no matter fields in this, and it corresponds to the ground state of our CFT, d-dimensional CFT. And then if we consider the thermal excitation of this CFT, we have to put a black hole in our bulk space. So we consider the ADS Schwarzschild black hole spacetime. And then I will show you some relationship between the holographic entanglement entropy and the black hole entropy we put here in our black hole spacetime, and then give the summary. Okay, now when talking about the holography, we always comes up with a famous example, the ADS CFT correspondence, which means n equals to 4 super Yang-Mills conformal field theory corresponds to, or we say is due to, an ADS 5 times S5 type 2B string theory, or just roughly speaking. Now, here I have a d+1 dimensional, or here in my case I have a d+2 dimensional ADS spacetime, the bulk geometry here. Now, in the ADS geometry, in the ADS spacetime, I can always find a conformal boundary. Here on this boundary, where z equals to 0, there's a d+1 dimensional boundary here. And our CFT, the conformal field theory, lives on here. Okay, now if we want to see the entanglement entropy of this conformal field theory between this area A and the outside of this area, we use the RT formula, the Liu-Takayanagi formula listed here, to calculate the entanglement between this area and this complementary area here. So on this area, I have the entangling surface, partial A here. And this area epsilon A means there's a minimal surface epsilon A in the bulk, in the ADS spacetime, and on this conformal field boundary, it coincides with this entangling surface. So the entanglement entropy here is proportional to this area. And this Gn d+2 means the Newton constant in the d+2 ADS spacetime. Okay, here's how the method how we calculate the entanglement entropy here. Okay, so the main problem is how do we calculate this area and guarantee that this surface is a minimal surface. Okay, so now given the metric in the bulk, our ADS spacetime, ADS spacetime, we have a general metric here. So now we have to find the induced metric on this minimal surface, which is written like this. Okay, it's just the induced metric of one-dimensional lower surface in this bulk geometry. Okay, so once I have the induced metric, the area of this minimal surface is by calculating this functional. Okay, and then our setup is there are two kinds of coordinates we use to represent the ADS space-time. The one is the global metric, and another is the Poincare coordinate here. And for simplicity, we use the Poincare coordinates in our later calculation. Now we can parameterize this minimal surface, this D plus D. Oh yeah, this is a D-dimensional minimal surface using x1 to xd, and then here x1 is we will restrict the x1 to minus a, and a, which is on this point is the entangling surface on the CFT, and we have the translational symmetry in other d-1 directions. So to parameterize this minimal surface, we use z and x1, and then we know that z only depends on x1. So our area, the determinant of Hij, the induced metric, now can be written in this form. And this is the holographic entanglement entropy in a pure ADS spacetime. Now, so our task is to find out this first derivative. And we can observe that this functional is not an explicit function of x1, so we can use canonical transformation to find the Hamiltonian of that function, this functional here. And then see the Hamilton equation, we can get this first derivative. It looks like this. Here the z star is the point that the minimal surface turns around. So it's the farthest point to 0 here. Okay. Now here is how we how can I say the boundary conditions we imposed here. The entangling surface locates on a and minus a of this x1, and I have the turning point where the first derivative of z equals to 0 at z star, this point. So this a determines the z star, and their relationship can be written in this integral here. Okay. And we have the d-1 translation symmetries. So from x2 to xd on these all directions, we put the volume as capital L to the d-1. Okay. So after some calculation, we can find out the entanglement entropy of a pure ADS spacetime, which corresponds to the ground state of a CFT, a d-dimensional CFT. Now looks like this. Here we can observe that there are two terms here. The first term is a divergent term, and the second term is a finite term. And we can observe that the dimensional of this, of the first divergent term, is proportional to, proportional to the x1 here, which means the surface of this entangling surface. And the subleading term, this finite term, is proportional to the volume of our bulk. Okay. Now we want to see the thermalization of the CFT here, so we have to put the ADS Schwarzschild black hole. So the ADS Schwarzschild black hole, the matrix looks like this. We have the horizon located at z edge here. Okay, and then we have the same setup as the pure ADS space-time. We use the same boundary conditions. We use the same parameterizations. But here, the first derivative of this z now becomes different. Now it looks like this. We have this black hole factor here. And the boundary condition, the relationship between the boundaries conditions can be written as like these forms. We have the black hole factor here. So what's the difference when we consider the a black hole located, the horizon located here? Is now we have the same divergence term, and we have this term, and we have another two finite terms here. And here the B is the ratio of the horizon and this turning point here. Okay, so now we look at an extreme limit, which when B equals to 1, our turning point touches the horizon. So this boundary tells us that when we consider that Z star goes to Z edge, this term will also be a divergence term. So we have this divergence term and this divergence term, and then these two finite terms. And you can observe that this divergence term is proportional to the Z edge to the power of D, which is proportional to the entropy of this black hole. Okay, now you can look like this. So when A goes to infinity, this Z star goes to the Z edge here. So now we have calculated that this area, the B goes to 1, this limits the area of this mineral surface, and we can minus this epsilon L area is the straight line from our Z equals to 0 to Z edge. Now we can see the first divergence term disappears, and the second divergence term totally is the leading term is proportional to the black hole entropy here, and we have all these finite terms. And then after put the black hole here, we have two different kinds of minimal surface, and we can see this is an interpretation of this Araki-Lib inequality in quantum information theory. It says that when we consider the entanglement of two subspace and this is the how can I say it? You can calculate the difference between these two entanglement entropy, and its maximum is the entire density matrix entropy. Okay, so how here in our we have these two kinds of different minimal surface, which means this epsilon A is this SA, and this epsilon AC is this SAC. So when the case this A goes to 0, we have the entropy mainly contributed from the black hole entropy here. So another case is when is it equals to 0 is the case that these two, we choose the boundary that these two surfaces totally equal. Okay. Now here goes the summary. We have calculated the entanglement entropy of a ground state in a D+1 dimensional CFT, and we consider the thermal excited state of D+1 dimensional CFT, And we have say that it's a holographic interpretation of this inequality. And we have this kind of further discussion on is there any transition between two kinds of topologically different integral entropy, and or we can consider the boundary effect on this space. Okay, thank you.
Question and comment? No? Okay, if no more questions, then let's start with this speaker again.